You know that feeling when you see something scale incredibly well, like with language models, right? Where you just throw more data, more compute, bigger models at it, and performance just
Yeah,
skyrockets.
those scaling laws, they've been super powerful in areas like NLP and vision.
Yeah.
It's driven a lot of progress.
Exactly. So it makes you think, okay, can we just do that everywhere? Like, what about offline reinforcement learning, where you're learning from this huge pile of data you already have without getting to, like, try things out live?
Hmm.
Does that same just scale it up idea work for really complex stuff that needs, a long sequence of decisions?
Well, that's precisely the question we're digging into today. We're looking at this really interesting research paper, Horizon Reduction Makes RL Scalable.
Yeah.
The authors basically asked, look, can current offline RL algorithms crack these super complex problems if we just give them massive amounts of data and compute?
And, okay, here's the kicker, the spoiler right away. What they found is, while for a lot of the standard offline RL methods, even when they scaled the data up like 1,000 times more than usual,
Which is huge.
right, performance on the really tough tasks just hit a wall. It didn't scale like you'd expect.
Yeah, performance often just flattened out way below, perfect success. It suggested there was something more fundamental going on, not just needing a bit more data.
Okay, so if just piling on data wasn't the fix, what is the problem? The researchers have a hypothesis, this thing they call the curse of horizon.
Right, the curse of horizon. It's basically about the difficulty that crops up when the sequence of actions needed to get to the goal is really, really long. It affects how the system learns to judge future outcomes and how it learns the actual strategy.
So our mission for this deep dive is to unpack all of this. We'll look at why those standard methods kind of failed, get into the weeds of this curse of horizon, and then explore how some techniques, specifically ones that reduce the effective horizon, might actually be the key to making offline RL scalable for these hard problems. Get ready for some potential aha moments about AI scaling.
Yeah, it really shifts the focus, from just more is better to thinking about smarter algorithms designed for this specific kind of long-term complexity.
Okay, so let's start at the beginning. What is offline RL exactly? And why is scaling such a big deal here?
So offline reinforcement learning, it's all about learning a good strategy. We call it a policy, using only a data set that's already been collected. You can't interact with the environment while you're learning.
Right, like trying to learn surgery just from videos, no practice allowed.
Exactly. And the main challenge is learning from that fixed history without accidentally learning to do things that look good in the data but are actually terrible, maybe because they weren't explored much in the original data collection.
You're stuck with what you've got. And that's super relevant, right? Because in the real world, robotics, manufacturing, maybe healthcare, getting new data by trial and error can be crazy expensive or slow or just too risky.
Absolutely. So being able to learn effectively from huge existing data sets is potentially transformative.
Okay. And scaling here isn't just about doing a bit better on easy tasks.
No, not really. It's about getting substantially better performance, specifically on tasks that need a long chain of tricky, connected decisions to succeed. Think deep, complex sequences, not just like more variety.
Right, tackling the really tough multi-step puzzles. So how did the researchers actually test this? What were the tasks?
They used a set of pretty challenging simulated robot tasks from this benchmark called OG Bench. These were specifically picked because they need complex, long-horizon thinking.
Okay, tell us about them. What makes them hard?
Well, there's one called Cube Octuple. A robot has to manipulate and stack 8 different cubes in a specific order.
8 cubes sequentially. Okay.
Yeah. Then there's Puzzle 4x5 and Puzzle 4x6. These are like those lights out games. But a robot arm has to press the buttons. You need a careful sequence to solve it.
Combinatorial puzzles with a robot. Got it.
And the last one is Humanoid Maze Giant. A complex humanoid robot has to find its way through a really big maze.
Wow, okay. Those definitely sound like they need a lot of steps and planning ahead.
Exactly. The paper describes them as needing highly complex, long-horizon, sequential decision-making. That's the key phrase.
And the data, how much did they scale that up?
This is where it gets wild. They generated data sets for these tasks with up to 1 billion transitions.
1 billion.
Yeah. For comparison, typical offline RL research often uses data sets around, say, 1 million transitions. So this is literally 1,000 times bigger.
That is a serious stress test.
It really is. And importantly, they did something else.
Yeah.
They used kind of simplified versions of the environments to isolate the core RL challenge.
How so?
They used low-dimensional state inputs, basically. Numbers representing the state, not complex camera images.
Yeah.
And they gave the agent a clear representation of the goal, an oracle goal.
So no struggling with vision or figuring out what the goal looks like?
Right. It strips away those other hard problems and forces the focus purely on the sequential decision-making part. Can the algorithm learn the long sequence of actions, even with perfect state info and massive data?
Okay, so the stage is set. Tough, long tasks, enormous data, simplified perception. What actually happened when they ran the top offline RL algorithms on this?
This is the core finding. They took several well-regarded state-of-the-art methods, things like IQL, SCC plus BC, CRL, Flow BC, and tested them, cranking up the data from 1 million all the way to 1 billion.
And did performance just climb and climb?
Nope. That's the surprise. They found performance on these harder tasks really struggles to scale. It tended to quickly plateau well below the optimal success rate, way below 100%.
Plateaued, even with a billion examples.
Yeah, you can see in the paper's figures, like figure 1 and 3. The learning curves just flatten out. And for the absolute hardest task, cube octuple, some methods just completely failed, like zero success, even with all that data.
Wow, that really goes against the usual scaling intuition, doesn't it? Why wouldn't more data help if the data, in theory, shows how to solve the task?
It's a really critical point. And the researchers were careful. They tried to rule out the simple explanations.
Like maybe the tasks are just impossible, even with that data.
They checked that. On easier versions, like stacking only 2 cubes, cube double, or a smaller puzzle, puzzle 4 by 4, these same algorithms could actually do pretty well, sometimes even mastering them.
Okay, so the algorithms can learn something from the data on simpler versions.
Right. And, spoiler alert, they later show that different methods can get some success on the hard tasks. So it's not that the tasks are fundamentally unsolvable with this data.
Okay, not impossible tasks. What about just needing bigger models, bigger brains?
Good question. They looked into that too. They'd scaled up the neural network size for one of the methods, SAC plus BC, quite dramatically up to nearly 600 million parameters.
Did that break the wall?
It helped a bit on some tasks, but the paper concludes it was not sufficient to master the tasks, especially the really hard ones like cube octuple. Performance still saturated, and sometimes even got a tiny bit worse with the absolute biggest models.
So more compute helps a little, but it's not the magic bullet.
Seems not. And they didn't stop there. They did extensive hyperparameter tuning, messing with policy types, ensemble sizes, regularization strengths, learning rates, how often target networks update, how long they trained, you name it.
Really, threw the kitchen sink at it.
Pretty much. And the conclusion was pretty stark. None of these changes substantially improves scalability or asymptotic performance across the board.
Huh. So it really feels like it's not just about needing more power or fiddling with the knobs. The problem is deeper.
That's the strong takeaway from this part of the research. The limitation seems baked into how these standard algorithms work,
Yeah.
especially when faced with these really long horizon challenges.
Which brings us right back to their main idea, this curse of horizon. Let's really unpack that. What does this curse actually involve?
So the core idea is that the difficulty just blows up as the required sequence of decisions gets longer. And this curse hits RL systems in 2 main ways. First, how they learn to evaluate future outcomes, that's value learning. And second, how they learn the actual sequence of actions, that's policy learning.
Okay, let's take value learning first. Lots of these algorithms use something called temporal difference learning, TD learning, right? To estimate how good it is to be in a certain state or take an action. How does the horizon mess that up?
TD learning basically works by updating the value estimate for your current state based on the estimated value of the next state you land in. The issue the paper points out is that this target value, the estimate for the next state, is itself imperfect. It's biased.
Because it's just another estimate.
Exactly.
Yeah.
And these little biases, these errors, they accumulate over the horizon. Imagine a tiny error in estimating the value 1 step ahead. Now imagine you need to string together 100 steps. That error gets compounded again and again and again.
Like a game of telephone. The message gets distorted more and more the longer the chain. So the further away the actual reward is, the more these errors pile up, making your initial value estimates totally unreliable.
Precisely. They used a neat little illustrative task to show this, called combination lock. It's designed to require a very specific, long sequence of actions. One wrong move and you're back to the start.
Perfect for isolating the long sequence problem.
Right. And they ran experiments comparing standard 1-step DQN, which relies heavily on that immediate next step value, with a 64-step version, which looks much further ahead.
Okay, what did they see?
They found that the one-step DQN had significantly larger Q errors. That's the difference between the learned value and the true value of being in a state. Much larger errors than the 64-step version, even when their immediate one-step TD errors looked similar.
So the accumulated error over the whole sequence was way worse for the one-step method.
Exactly. And they showed graphically how these Q errors get bigger the further you are from the end goal. It directly links this bias accumulation to the horizon length.
Yeah.
And this accumulated bias strongly correlated with poor performance on longer tasks.
And just tweaking things like learning rates or model size didn't fix this fundamental bias buildup.
Apparently not. Figure 8 in the paper suggests these standard tweaks don't really get at the root cause of this bias accumulation. It seems like a fundamental problem with standard TD learning over very long horizons.
Okay, so curse number 1. Value learning gets messed up by accumulating bias. What about the second part, learning the policy itself, deciding what action to take?
Yeah, even if, hypothetically, you had a perfect crystal ball for values, just learning the right sequence of actions over a long horizon is still incredibly hard.
Why is that?
Think about it. The single best action to take right now often depends intricately on navigating the entire complex path through the state space all the way to that distant goal, especially in goal-conditioned tasks. Your first step has to be aware of the entire sequence needed to succeed, maybe hundreds of steps later.
It's like that first chess move depends on anticipating the checkmate. Many moves down the line. The complexity of the whole future is packed into that initial decision.
That's a great analogy. The mapping from your current state to that optimal first action becomes incredibly complex when the goal is far off. The paper mentions hierarchical policies as one way to think about tackling this.
Hierarchical, like breaking it down.
Yeah, exactly. Imagine having a high-level policy that just decides on intermediate goals, like get to that doorway, and then a low-level policy figures out the steps to reach that doorway. Each policy has a shorter, simpler task.
Reducing the effective horizon for each part of the policy. Like planning a road trip by first picking major cities, then navigating within each city. They even mention it's like chain of thought in language models, right? Breaking down complex questions.
Precisely. Decomposing the problem reduces the complexity each individual policy has to handle.
Okay, so the curse hits both values, bias, and policies complexity when the horizon gets long. If the horizon is the core problem, then can we just shrink it? Can we reduce the horizon somehow?
That's exactly the promising path the paper explores next. If the long horizon is the bottleneck, then techniques designed explicitly to reduce the effective horizon should help things scale better, and the results they show are pretty compelling.
Okay, let's hear it. How did horizon reduction work in practice?
First, they tackled the value horizon. They compared standard SAC plus BC with a version called n-step SAC plus BC. Instead of just using the value estimate from the very next step, one step, the n-step version uses the actual rewards collected over, say, n steps, plus the value estimate from step n.
So you're looking further ahead before you rely on an estimate, cutting down the number of times errors can compound.
Exactly. You're reducing the number of TD steps needed for information to propagate back from the reward. And what they found was that using these n-step returns substantially improves scalability and even asymptotic performance on many tasks.
Wow, okay, so just changing how you calculate the target value helps a lot. That really supports the bias accumulation idea.
It does. Then they looked at policy horizon reduction. They compared standard flow BC, which learns one flat policy, with hierarchical flow BC. The hierarchical version learns a high-level policy to pick sub-goals and a low-level policy to reach them.
Breaking down the action sequence, did that help?
Yes, significantly. It significantly improves performance, especially on that really tough cube octuple task where the standard version got basically zero success. Making the policy hierarchical made the problem manageable.
Okay, so reducing the value horizon helps with bias, reducing the policy horizon helps with complexity. What if you do both? Combine them.
And that brings us to the main method they propose in the paper, SHARSA, and an enhanced version, double SHARSA.
SHARSA. Okay, break it down for us.
So the goal with SHARSA was a simple, scalable way to reduce both the value and policy horizons simultaneously. They built it using fairly straightforward components. Behavioral cloning, specifically flow BC, because it's good at modeling complex action distributions, and SARSA for the value learning part. These tend to be a bit less finicky with hyperparameters.
Okay, simple blocks. How does it tackle the horizon problem?
Okay, for the high-level policy, the part that chooses sub-goals, SHARSA does something interesting. Instead of trying to learn a direct mapping using gradients, it uses rejection sampling.
Rejection sampling, how does that work?
It basically samples a bunch of potential subgoals from a learned behavioral cloning model, then uses a high-level Q function, which estimates the value of reaching those subgoals, to evaluate them, and it picks a subgoal with the highest estimated value.
Ah, so it generates possibilities and then selects the best one based on value, rather than trying to directly compute the best action gradient.
Exactly. And they argue this is especially useful when parts of your state are discrete, like the buttons in the puzzle tasks. Gradients might not even be well defined there. Their tests showed rejection sampling worked better, particularly on those puzzle tasks.
Makes sense. And how does the value learning work for these subgoals?
The high-level value function is learned using SARSA with n-step returns, explicitly reducing the value horizon for judging subgoals. Oh, and an interesting side note, they found using a binary cross-entropy, BCE, works better than the usual regression loss for these value functions, especially for long horizons.
Oh, a different loss function. That's subtle but important.
It seems so. Now, for the low-level policy, the part that actually executes actions to reach the chosen subgoal standard SHARSA just uses behavioral cloning.
Okay. And double SHARSA.
Double SHARSA adds another layer of this rejection sampling idea, but for the low-level actions. It samples potential actions from a low-level BC model and uses a low-level SARSA value function, also learned with n-step returns, to pick the best action to take at each step towards the subgoal.
Whoa. So double SHARSA is doing this sample and evaluate thing at both the subgoal level and the individual action level, using value functions that are specifically designed to handle reduced horizons. How did that perform?
That was the big winner. The paper says double SHARSA showed the best scaling behavior and asymptotic performance out of all the methods they tried. Crucially, it was the only method that achieves non-trivial performance on all 4 tasks, including that killer cube octuple task where others just failed completely.
That's a really strong result. It really seems to back up their whole hypothesis, tackle the horizon explicitly, maybe hierarchically like SHARSA does, and that's how you unlock scaling for these complex offline RL problems.
Yeah, it really shifts the conversation. It's not just about bigger data sets or bigger models. It's about architectural choices and algorithmic designs that are smart about handling this temporal complexity, this long horizon.
Okay, let's zoom back out then. What's the big picture takeaway here for you, the listener, thinking about where AI is heading?
Well, I think the main thing is that for certain kinds of problems, these long, complex, sequential decision tasks where you only have past data, just throwing more data in compute at standard methods isn't a guaranteed win. That cursive horizon is a real
Theory. It's actually stopping us from applying offline RL effectively to really important, complex, real-world stuff, like robots doing intricate assembly or planning complex supply chains.
Exactly. And the implication is that researchers and maybe even engineers building these systems need to focus more on algorithms that explicitly manage that horizon. Techniques like using multi-step value updates, building hierarchical structures, or these SHARSA-like methods seem necessary to get true scalability on these kinds of challenges.
It really suggests that cracking complexity in AI might demand more than just more stuff. It might require fundamentally different ways of breaking down problems and learning over these extended timescales.
Yeah, algorithms designed with the horizon problem in mind, not just hoping to overpower with brute force scaling.
So this has been a fascinating deep dive into why scaling isn't always the answer in offline RL and the surprising effectiveness of tackling the horizon directly.
Yeah, we saw how standard methods hit that ceiling, even with massive data. We unpacked the cursive horizon, both the value bias and the policy complexity. And we saw how techniques designed to reduce that horizon, like n-step returns, hierarchy, and especially SHARSA, offer a really promising way forward.
And the paper doesn't pretend this is the final word, right? It ends with a call for research. This is still an active area. They're asking big questions. Can we get rid of TD bias completely? Can we build hierarchies that go even deeper? Are there fundamental theoretical limits we still don't understand?
Absolutely. It shows there's still a lot of work to do to build RL systems that can truly handle the most complex sequential problems reliably and scalably.
Which leaves us with a final thought for you to chew on. Think about the complex tasks you deal with. Maybe planning a big project, learning a really difficult skill, even navigating a tricky personal situation. A lot of these involve long chains of decisions where one step depends on the next. Could that horizon, how far away the final goal feels, how many steps are involved, be the hidden reason those things feel so hard sometimes? If the key for AI in this context wasn't just more data or bigger models, but actively breaking down the problem into smaller, manageable time chunks, What might that suggest about how we could approach tackling other big, complicated challenges?
It really makes you think about the structure of complexity itself, doesn't it? Beyond just how big the problem is.
Something to think about. Thanks for joining us for this deep dive.